Hello all, welcome to the lecture. In the last lecture, we looked into the hyperfine interactions of the methyl radical, which can be also represented as CH3 dot. So, we saw that the A, which is the hyperfine coupling constant. So, this A or the hyperfine coupling constant can be obtained from experiment, and this A is related to the unpaired electron density. So, A is related to the unpaired electron density, which is given by rho. So, in other words, we can write A is proportional to rho, and because A is proportional to rho, we can write A equals R times rho, where R is the proportionality constant. So, this value of R can be obtained if we know the values of A and rho. In other words, the value of R can be obtained using the known values of A and rho for any suitable system. So, let us take the system of this hydrogen atom. For this hydrogen atom, A equals 0.05 T and rho equals 1. So, the electron density, that is rho, for the unpaired electron in hydrogen atom is 1, because the hydrogen atom has only one electron and it interacts with only one proton. So, thus we can write R equals A divided by rho. So, that is 0.05 T, because rho equals 1, and because R is given by 0.05 T, we can go back to this equation and write A equals 0.05 T times rho. Now, for a particular system, let us say we take the system of methyl radical. So, for a particular system, the value of rho can be calculated using this expression. So, let us say we talk about the methyl radical or CH3 dot, and for methyl radical A is given by 23 millitesla. So, that means 23 times 10 to the power minus 3 T. So, we can write 23 times 10 to the power minus 3 T, that is equals to 0.05 T times rho. So, from here we get rho equals 0.046. So, now you can ask that what does this value of rho indicate? So, this value of rho, that is 0.046 in the case of a methyl radical, indicates that the electron density on each atom, for this case is a proton, is 0.046. Thus, the total electron density, or let us write total electron density, is given by 3 times 0.046, that is 0.13. 0.138. This is because in the methyl radical there are 3 protons, and the remaining density, that is, if the total density is 1, then 1 minus 0.138 equals 0.862. So, this remaining density is on the carbon atom. So, what does this mean? This means that the unpaired electron is not localized on the carbon atom. In other words, it is delocalized. It is delocalized such that over the molecule it is spending approximately, let us say this we can write as 0.14. So, it is delocalized over the molecule such that it spends 14% time on the hydrogen atoms, and the rest, that is 86% time on the carbon atoms. So, now let us focus on the geometry of this methyl radical. So, the methyl radical, that is C, there are 3 hydrogens and an unpaired electron. So, this can have 2 possible geometries. So, one is the pyramidal geometry. So, if I draw this looks like this, and this is where the unpaired electron is. The other possibility is a planar geometry. So, I can draw it this way. So, this is the plane, and this is where the unpaired electron is. So, in the pyramidal geometry, the electron is in an sp3 hybridized orbital. On the other hand, in the planar geometry, the electron is in a pure p orbital. So, one has to know the value of A C, where C stands for carbon. That is, A C is the hyperfine coupling constant of the electron with the carbon nucleus or the carbon atom. So, this is the hyperfine coupling constant of the interaction. So, electron interaction with carbon nucleus. So, we need to know the value of A C. So, for a pyramidal structure, the electron is in the sp3 hybrid orbital. In other words, in an sp3 hybrid orbital, there is 25% of s character. So, that means the A C should have an appreciable value if the geometry is pyramidal, because if it is in s orbital, then the electron spin can interact with a nuclear spin. So, in an sp3 hybrid orbital, it has 25% s character. That means, the A, the hyperfine coupling constant, is not 0, but has an appreciable value. On the other hand, for the planar structure, the unpaired electron is in the pure p orbital, and as we know, the pure p orbital has a node at the carbon nucleus. So, this should make the A C equals 0, and because it has a node, so there should be no interaction between the electron and the nucleus, and that is the reason why A C equals 0. So, we cannot obtain the value of A C if we take a CH3 radical, where it is that 12 carbon. This is because the I of 12 carbon is 0, and because the I of 12 carbon is 0, it does not involve any hyperfine interaction. So, in order to find the structure, we need to know the value of AC, but we cannot find the value of AC if we use a 12 carbon methyl radical. So, the way out is to use the 13 C isotope of the methyl radical. So, the use of the 13 C isotope, that is the 13 C methyl radical, would enable us to find the value of AC. And we will see, we will have 4 times 2, that is 8 hyperfine structures in case of 13 C methyl radical. This is because we already had 4 hyperfine structures for 12 C, but the carbon nucleus was not interacting. But now we have a case where not only the 3 protons are interacting with the unpaired electron, but the 13 C nucleus is also interacting, and the I value of 13 C equals half. So, for the number of lines just coming from the interaction of the unpaired electron with the 13 C nucleus is 2 n I plus 1, which is given by 2, n is 1 because there is 1 carbon nucleus, times half plus 1. So, 2 cancels here. So, we have 1 plus 1 equals 2. So, if we did not have this carbon 13 nucleus, we had 4 hyperfine structures. Now, we can think these 4 hyperfine structures would individually split into 2. So, we will have 4 times 2, that is 8 hyperfine structures, and this is how we can in principle obtain the value of AC. So, from the experiment, it comes out that the AC has a very, very small value. Or how can we find that? So, let us say we have this spectrum, which is the ratio of 1:3:3:1, and this was for the 12 carbon methyl radical. Now, if we have a 13 carbon methyl radical, these peaks would split. So, ideally I should get something like this, and this splitting, this gap will give us this AC. So, experimentally it can be seen the value of AC is very, very small, although AC is not exactly equal to 0. So, this means that within this experimental error bar, the hyperfine interaction is negligibly small. So, this ESR evidence goes in favor of the planar structure, and that is because for planar structure, as I had mentioned before, AC equals 0, and from experiment we do not exactly find AC equals 0, but AC is very, very small, which tells us the hyperfine interaction is negligible. So, though we have already used it when we talked about this methyl radical, after this we would formally see what happens when different nuclei with different values of I are present, as long as I is not equal to 1. So, this is the last thing we would see. So, we have seen that the number of hyperfine lines in the ESR spectrum is caused by the interaction of unpaired electron with the nuclear spin. Now, let us say there are n number of nuclei. and this n number of nuclei has spin I. So, what we know is that the total number of hyperfine lines is given by 2 n I plus 1. Now, if there are different nuclei present with different I values, let us say I have few nuclei with I equals half, few other nuclei where I equals 1 and few other nuclei with I equals 3 by 2. So, we cannot use this formula, that is 2 n I plus 1. In such a scenario where we have different nuclei with different I values, the number of hyperfine lines is given by this pi. This is a symbol where you have to multiply of I, this is multiplication of all I, 2 n I plus 1, where this n I is the number of nuclei with nuclear spin I equals I. So, to understand this in a better way, let us look into a couple of examples. So, the first example we take is a radical, that is CH2Cl, and now the I of H we know is half and the I of Cl is 3 by 2. So, we can see the unpaired electron will interact with 2 of the protons where I equals half and 1 chlorine where I equals 3 by 2. So, if I want to find the number of hyperfine lines using this formula, what we will have for interaction with proton, we have 2 times 2 protons times half, that is the value of I for proton, plus 1, but then we will multiply because we have this symbol here. This is 2 times we have 1 chlorine times I value of chlorine, that is 3 by 2 plus 1. So, if I do the math properly, what I get, this is 2 plus 1, that is 3 times this is 3 plus 1, that is 4. So, we should have 12 hyperfine lines. Now, let us take another example. We take the example where we have 13C H D2 radical. So, we should remember that in the first case this was 12C, and because it was 12C, we did not take into account the interaction of the unpaired electron with the carbon nucleus, because I equals 0 for 12C. But in the second example where what we are talking about, it is 13C. So, I of 13C equals half. So, I of 13C equals half and I of proton equals half and I of deuteron equals 1. So, if I want to find the number of hyperfine lines, what we have here. So, let us first consider the interaction of the unpaired electron with the 13C nucleus. So, that is 2, there is one such nucleus times I value of half plus 1. So, this is coming from the 13C. then we will multiply and we will look into the proton case. So, that is 2 times 1 proton times the I value of proton, that is half plus 1. So, this is where I am looking at H, and finally, we will multiply with 2, then there are 2 deuterons with I value of 1 plus 1. So, this is where I am looking at this D 2 case, and in total we have 13 C H D 2 radical. So, we can write this 2 cancels, that is 1 plus 1 is 2 times the same thing times 2 times 4 plus 1, that is 5. So, the number of hyperfine interactions we will have here is 4 times 5 equals 20. So, this brings us to the end of this lecture and also to the end of electron spin resonance spectroscopy or ESR spectroscopy.